All right, so in continuing on with the examples in the supplemental text for basically finding either the current through the inductor or the voltage across the capacitor, the total responses for those within a parallel network, we're actually going to go through and look at basically example 2 and also example 3. We're going to knock these out together, and they're actually quite short, but there's one portion of it in terms of the initial conditions that we really need to pay quite close attention to. So for this one, guys, we're going to look at the integral form for, first, and then just like we did with the series elements, for example 3, we're going to go ahead and utilize the derivative form and prove that both of them produce the same form of VC of S. Now, for this problem, we wanted to find the capacitor voltage, and like I said in the prior video, that when we have the KCL equation, we know because they're parallel elements that they're all going to have the same voltage. So once we expand that KCL equation by the current voltage characteristics, everything is put in terms of voltage, just immediately. So we could even go back and say, find the inductor's voltage, and all we would be doing is actually finding the capacitor's voltage directly. So you could either say it one way or the other, but let's just say capacitor voltage just for the time being here, just because in this case, we actually have to consider the second initial condition for that capacitor, that change in that initial condition for that capacitor's voltage. So for this one, switch open at t equals 0. Here we got 1.5 ohms. We have a capacitor with 111 millifarads, 1 Henry inductor, and then a 4 amp source. So switch opens at t equals 0. So we're going to look at t less than 0 first and go through and find that initial condition. Now, just like in the previous problem, we had a short that was introduced in the middle when the circuit was sitting in steady state. Inductor is acting like a short, capacitor is acting like an open circuit. So just like before, here 100 volt source with 50 ohms of resistance. Basically that current's going to leave. It's about 2 amps. It's going to go through, it's going to get to that 1.5 ohm resistor. It's going to say, nah, I can't deal with that. Go right past that. It's going to look at the open circuit here and say, no, I'm not going to deal with that either, and it's going to dump right into the short. Same thing over here, 4 amps, it's just going to see the short and dump all of that 4 amps into the short. So what we get is a combined effect of 2 amps plus 4 amps that gives us 6 amps for that initial current going through the inductor. Capacitor, since it didn't have any current going to it, so no charge went to it, so there was no potential difference built between the anode and the cathode. In this case, we have 0 volts across it too. So let's now take a look at t equals 0 plus, because we know we have to at some point consider basically the change in the initial condition right here. Now, for here, IR of 0 plus, IC of 0 plus, IL of 0 plus. Now, in this case, VC of 0 plus is still 0 volts, IL of 0 plus is equal to 6 amps, and man, I really miss being in the classroom where I can just ask you guys questions, but I can't ask you guys questions necessarily to a camera. I could, but then what's the point? Anyway, we'll be talking about some of these questions when we're actually doing the Microsoft Teams videos. Now, considering here, I'm going to go ahead and find the change in the initial condition for the voltage across the capacitor, because we're going to come back and use that in just a bit. And we're going to see a really cool correlation with this, guys. Really cool correlation. So in this case, we have to find dVC naught plus dt, and that's equal to IC of 0 plus. So what would IC of 0 plus be? Remember that the voltage can instantaneously change. The current through the capacitor can instantaneously change. So we have to find this by evaluating the KCL equation. And that KCL equation evaluated at t equals 0 plus, IR of 0 plus IC of 0 plus IL of 0 plus, and that's equal to 4 amps. But IR of 0 plus, that's VR of 0 plus divided by R. Well, that resistor's voltage is going to be held to basically be 0, because the capacitor cannot instantaneously change its voltage. And so it's driving basically the value of the inductor as well as the resistor to have a value of 0 volts across it. So there you go. Bam, that was gone. No current. No current is actually going to go through the resistor because the capacitor is holding that value to be 0 volts and preventing any current from even going to that resistor at t is equal to 0 volts. T is equal to 0 plus. That's astonishing. That's an amazing thing to see, that the cap is actually going to prevent any current from going into that resistor. Now, IC of 0 plus, that's what we're looking for. IL of 0 plus, we know is 6 amps. So 4 amps over onto the right hand side, we pull that 6 amps over to the side, we get IC of 0 plus is equal to negative 2 amps. Negative 2 amps. Well, by passive sign convention, we know that the voltage is defined in the orientation of positive to negative because of the way that the book actually gave us that orientation. So that means by passive sign convention, currents have to move from positive to negative. So what's really happening here, that current through the inductor cannot instantaneously change. And that has to say 6 amps. So we still got 4 amps that's coming in and going through there, but once it gets down to the bottom right here, 4 amps cycles back to the 4 amp source, and then 2 amps actually goes back towards the capacitor. And since no current can go to the resistor, this current, what it's doing is actually going into the negative terminal of the capacitor, and in fact, that is opposite of how we defined IC of 0 plus by passive sign convention up front. So in fact, actually, we do get negative 2 amps right here. So you guys have to be very, very careful. Once again, think intuitively about this, because that current's going into the negative terminal and going against how IC of 0 plus was actually defined in this problem. So be very, very, very careful on that, because if you don't, you're not going to get this negative 18 right here, and we're going to see in just a sec why that is so, so important to us. Okay, now let's take a look at t is greater than 0. We're going to look at the integral form first, and then we're going to prove that the derivative form produces the same value of Vc of s. So let's check this out. And if any of you guys are having trouble seeing the green on here, let me know, and we'll make sure it's clear. You should be looking in the supplemental text. This is example 2 and 3 in the parallel example section. So let's take a look here. Let's develop this differential equation, then let's solve the sucker. So IR of t, IC of t, and IL of t. IC of t plus IR of t plus IL of t is equal to 4 amps. So guys, once we expand this by those current voltage characteristics, the whole entire equation is already in terms of the voltage that we want, because Vc of t is equal to VR of t, and that's equal to VL of t. And so if we go ahead and just take the Laplace transform directly, after going ahead and putting this into a standard form by dividing through by c, notice right here we got that coefficient of 1 over RC and also of 1 over LC. Once we go ahead and take the Laplace transform, we get s times Vc of s minus Vc of 0, that we know is actually going to be 0 up front, plus 6 times Vc of s, plus 9 times Vc of s divided by s. Remember that when we take the Laplace transform of the integral, get Vc of s divided by s, and then these two constants over here basically are divided by s as well. So once we do that, we multiply both sides by s. And once we do that, we actually get rid of the denominator s's, and then actually get everything in terms of s squared. So s squared plus 6s plus 9 times Vc of s, and that's equal to negative 54, plus 36, and that's equal to negative 18. We've seen negative 18 in this problem already. But the nice thing is we don't have to do partial fraction expansion on this problem, because here we have negative 8. When we solve for Vc of s, we get negative 18 over s plus 3 squared. And because of that, there's no reason to actually go through and do partial fraction expansion, because this we can readily take the inverse Laplace transform of. And when we do that, Vc of t is equal to negative 18 times t times e to the negative 3t volts. Now here's the thing. In the book, I go ahead and do the partial fraction expansion and actually show that one of the terms that we do for repeated roots, actually that coefficient when we actually do the calculations, comes out to be equal to 0 anyway. So it just goes to show that if we have a constant in the numerator for this one right here, then we actually don't have to do the partial fraction expansion and just go ahead and take the inverse Laplace transform directly. So VC of t actually is equal to negative 18 times t times e to the negative 3t. Now, what about if we said utilize the derivative form? And I'm going to be testing you guys on how to basically prove these out, basically between the integral form as well as the derivative form. Now with the derivative form, all we had to do was take this guy right here, and by taking its derivative, we actually render a second order differential equation in which the constants on the right hand side basically get canceled out, and then we get basically, once again, putting it in the standard form, we get d squared vc of t dt squared plus 6 dvct dt plus 9 vc of t. And those constants go away when we take the derivative, and so that's equal to 0. So we take its Laplace transform and we expand it out, but because we have vc of 0 plus on either side here, both of those are going to be 0 because that initial capacitor voltage was 0, and then that held to be the same for t is equal to 0 plus. But we have a change in the initial condition. Here, v prime is 0 plus. We move that over to the other side, just like right here. Combine like variables of VCS. We get our characteristic equation. But what was v prime of 0 plus? We derived it, negative 18. There it is, guys. And then, therefore, comes out to be VC of S is equal to negative negative 18 over S plus 3 squared. That satisfies VC of S for both of those. So they produce, either form actually produces the same form of VC of S. Now, in that section, I'm going to tell you guys something I want y'all to look at. I'm going to ask this in a Microsoft Teams meeting. So, in this case, why did we actually get the same form? By using different initial conditions. And I want to hear your answer on that. So, now we've actually gone through the 6 different types of examples for series and also parallel. We're now ready to start working homework problems and extra problems and start moving towards test 1 material. So, going to look at you guys on Microsoft Teams. The first things I want you guys to answer for me is going to be why, with different initial conditions in either the integral form or the derivative form, we get the exact same form of VC of S. So I'll see you then.